Right folks, we're going to do the second part of the radioactivity flipped classroom project. I'm going to be talking about the atom. Atom being the building blocks of everything that we understand, and it's very important that you understand the nature of the atom before you understand any of the nature of the stuff that comes out of it, i.e. radioactivity. So I'm going to do a quick recap of the stuff that you should already know about the atom, and I'm going to build upon that to talk about radioactivity and where it comes from. So, some of this might not make much sense to you, but if you Google some of the terms in here, you'll be able to find out lots of information about how this works. We're going to start off by talking about something called Rutherford's experiment. There was a guy, a scientist called Rutherford, who wanted to find out what stuff was made of. So he did an experiment. It was using alpha radiation as a deflection experiment to find out what stuff was made of. And he found out that it was made of atoms, so with a solid positive nucleus in the centre and electrons going around the outside. Before Rutherford came along, however, the model that they had was the plum pudding model, and obviously once they discovered the atom, it completely rubbished the plum pudding model and replaced it. So that pretty much brings us to our current understanding of the atom, which we're going to go through now. So this is what we currently understand to be the atom. It's got protons in the centre along with neutrons, and it's got electrons going around the outside. The nucleus, which is the central section, comes from the same word to represent the control centre of the cell. The control centre, if you like, of the atom in the middle, the nucleus, has got these protons and neutrons in it. Protons give it charge, neutrons give it stability. Neutrons don't have any charge, they're neutral, hence the name. Protons are positive and electrons are negative. Now I want to move on a little bit, but it's important that you know where these positions are within the atom. It's important because it tells you a little bit more about radioactivity. Now, in the last section, I talked about alpha, beta and gamma radiation and what they're made of. But now I'm going to explain a little bit more as to the nature of them, using what they're made of. So you should know that the atom is made of bits, protons, neutrons and electrons. The middle bit, the nucleus, is made up of these protons and neutrons. Every bit has a mass and a charge. We say the electron has no mass because it has a negligible mass, a very tiny one, 1/1800th of an atomic mass unit. These are quite heavy. This isn't. So these ones travel very, very fast. These ones travel very, very slow. Charge on a proton, don't forget it's +1. It's neutral on the neutron, and it's -1 on an electron. When you add all these bits together, it starts to make a little bit more sense. Protons attract electrons because of the opposite charge, which makes them stick to the atom and they orbit around the outside. Neutrons act like glue. They stick the nucleus together and provide it some stability. Now we're going to move on to the next bit, and I'm going to talk about where these things come from. Now, radioactivity. Radioactivity is all about these things called isotopes. An isotope is a different type of an element. So this is the definition for it. An isotope is an atom of an element that has the same number of protons but a different number of neutrons. What it means by that is you can have loads of different isotopes of the same element. So let's just take the simplest one that we know, which is hydrogen. Hydrogen's got one proton and it's got one electron going around the outside. If you add a neutron into that, it changes its mass and makes it a little bit more unstable. But it doesn't change the fact that it's hydrogen. It's still got one proton and one electron in it, and it's the protons that tell you what the element is. So in that case, it's still hydrogen. So I'm going to use another example. I'm going to use helium. Here's my example. We've got a helium atom, elemental helium. It's got 2 protons, 2 neutrons and 2 electrons. There it is. If you add another neutron into the mix, you've got an extra neutron. That makes it slightly heavier, which also makes it a little bit more unstable. And we call that an isotope. So if it's got a different number of neutrons in it than normal, we say that's an isotope. Now, last time in the last video I talked about these 3 types of radiation, alpha, beta and gamma radiation. They are all very, very different, but you need to know where they come from. So, alpha radiation first off. Alpha radiation is 2 protons and 2 neutrons. We say it's a helium nucleus, it's just like the centre of that helium that we were talking about a minute ago. And it had electrons going around the outside. This one doesn't. It comes from a nucleus. So it doesn't come from a normal nucleus, like a helium nucleus or something. It comes from a really heavy one. So let's take something like uranium. You can't see this, but if you remember my lab essay, you'll know there's a periodic table over here. Uranium, there she is, has got 92 protons and 238 protons and neutrons. So let's just take that 238 for a minute. 238 protons and neutrons makes it very, very unstable. It's really, really heavy. So an element like that might emit radiation in the form of alpha radiation. It's just too heavy. So it groups up 2 protons and 2 neutrons and it sends them away from the nucleus at respectable speed. So this alpha particle has left the nucleus, making it a little bit more stable. Whenever something emits radiation, it's in a quest for it to become a little bit more stable. Beta radiation. This also comes from the nucleus. Now this might not make sense to some people because in the nucleus, you know the nucleus has protons and neutrons in it, but yet I'm telling you here, an electron comes from the nucleus. If you want to really know where it comes from, that's quite advanced, that's A-level physics, and you can Google that, you can find out for yourselves, but you just need to be aware that it comes from the nucleus, and when it does come out of the nucleus, it does make it more stable. This is a lot faster than alpha, as we talked about in the previous, and you need to remember how to protect yourself from that, but you can go back and watch the other video. And lastly is gamma. Gamma radiation is a high energy wave. Again, it comes from the nucleus, and in this case the nucleus just has too much energy. So rather than using all that energy to heat something up or whatever, it emits it as a high energy photon. So it's a wave, we call it. So this gamma ray that comes out of there allows this to become a little bit more stable by it losing some energy. Remember, this is not a particle. We've also talked about this. This is a reminder of the last video. In the last video we talked about the masses and charges, and the mass of a proton, 2 protons and 2 neutrons is obviously 4. So the mass number of an alpha particle is 4. This is what we should be more concerned with, the charge. We talked about how it's attracted to different electrical plates. In this case, alpha is +2, beta is -1, gamma is 0, because there's no particles involved. And we talked about these 2 different things. This is how damaging it is to cells at short range. So alpha's the worst, but it needs to get into your body. Beta's pretty good all round. Gamma's quite low, but it gets through pretty much everything, which is what this term means. Penetration is how easily it passes through something. So alpha doesn't, it just is rubbish, it doesn't go very far at all. Beta is fairly good, but it doesn't get through metal because it's an electron, and gamma gets through pretty much everything except thick concrete and lead. So, in the practical, if you wanted to detect what type of radiation you are going to be experiencing, stick something in the way of it. This is the easiest way to do it. If you put some paper in front of the source and it stops at paper, then it's alpha. Dead easy. Beta, if it passes through paper, no problems, but it's stopped by something like aluminium foil or something that's metal, then it's beta. You know it's beta. To identify gamma, it'll get through paper, no worries. It'll get through aluminium foil, pretty much no worries. But it'll be stopped by the lead, and we've got some lead shielding, so you can test gamma for that as well. It might even get through some of the gamma shielding if it's a particularly powerful gamma ray. So that's the easiest way to detect them, just by what absorbs them. If you're detecting radiation, it's blocked by paper, it's alpha, blocked by metal or aluminium foil, it's beta, and if it gets through pretty much everything, it's gamma. And then you know what type of radiation you're dealing with, and you can protect yourself from it. Okay? Now, in the next section of this video trial thing, I'm going to be talking about these types of radiation and how they die off. Obviously, when something's emitting radiation, it's not going to stay radioactive forever. So we're going to talk about how it decays, and we're going to talk about something called half-life. And no, that's not a computer game, even though it is. I'm not going to be talking about that. Okay, so I'm going to leave you with that. We've got some activities to do in the lesson based on this knowledge. If you didn't understand any of it, then feel free to ask any questions. You can do that on Edmodo, or you can come and ask me before the lesson. Okay, thanks.